The standard model of cosmology relies on the cosmological principle, the assumption that on a large enough scale, the universe is perfectly uniform. Mathematics defines the absolute limit of this structural homogeneity at 370 megaparsecs, known as the Yadav scale. Over the past decade, observational astronomy has mapped ultra-large-scale structures that stretch far beyond this expected boundary. Researchers have cataloged massive gigaparsec-scale formations, including the giant arc, the big ring, the giant ring, and the giant GRB ring. This graph plots structure size against redshift. The red dashed line marks the 370 megaparsec homogeneity limit. The newly discovered ring structures plot high above it, exposing a vast mathematical discrepancy. Mapping these coordinates reveals a heavy concentration of megastructures in the upper hemisphere, isolated near the North Galactic Pole. The data establishes a clear pattern. The foundational assumption of uniform homogeneity is directly contradicted by the physical mapping of the universe. The standard cosmological model attempts to absorb these anomalies using state-of-the-art simulations like Flamingo 10K, which models structure formation through gravity and dark matter. When researchers analyzed 10 independent fields from this simulation, they found 0 statistically significant matter clustering on these extreme scales. This chart measures the anisotropy ratio of these objects to determine if they are mere observational artifacts of thin data slices. The big ring measures 1.2 to 1. It is nearly perfectly isotropic in 3 dimensions, disproving the thin slice hypothesis. Theoretical physicist Boris Krieger proposes a radical alternative. These formations are not random gravitational accidents, but rigid geometric projections. His model assumes the spatial topology of the universe is a real projective space, organized by a mathematical mapping known as the Hopf fibration. A geometric fixed point suggests that structure formation follows a predictable underlying template, shifting the research focus from random initial conditions to global topology. To test this geometric premise, we examine the data at the specific distance where the structural anomaly is most concentrated, redshift 0.8. This diagram maps a triple nested configuration found at this coordinate. The big ring is enclosed by the giant ring, which is enclosed by the giant GRB ring, surrounding a void interior. The ratio between the outer and middle rings' radii is exactly 1.72. That number equates to the square root of 3. In the mathematics of plateau foams, this is the exact circumradius to inradius ratio of a regular tetrahedron, the basic structural cell of an idealized foam geometry. We can calculate structure ratios at completely different cosmic epochs to verify if this pattern is a universal constant. This chart compares nested structure pairs at 3 separate redshifts. Across distances varying by a factor of 25, a size ratio of roughly 2.2 consistently appears between the structures. Standard cosmology dictates that structure sizes must evolve dynamically over time as the cosmological growth factor advances. A precise redshift-independent geometric ratio indicates a static architectural template rather than gradual evolutionary growth. The mechanism driving this static architecture is the Hopf fibration, a method of mathematically decomposing a 3-dimensional sphere. This decomposition creates a continuous family of coaxial, nested tori that completely fill all spatial dimensions.
Topologically, any 2 distinct fibers within this manifold are inextricably linked, carrying a strict linking number of plus or minus 1. When astronomers map the sky, they are looking at flat, 2-dimensional redshift slices, cutting directly through these 4-dimensional mathematical structures. If that observing plane tilts at a slight 5-degree angle to the tori's axis of symmetry, the cross-section yields a series of nested, offset ellipses. The intersection angle dictates observed matter density. Steep cuts through the torus wall present as thick, clustered rings. Tangential cuts, grazing the surface, present as thin, isolated arcs. This geometric projection specifically accounts for the morphological asymmetries documented in the giant arc and the big ring. The massive void regions mapped between the giant ring and big ring perfectly match the empty interiors of the topological tori. The specific physical asymmetry, structural branching, and exact void separation seen in the data are the precise geometric signatures of a sliced Hopf torus. If the template is purely topological, a physical force must compel baryonic matter to strictly follow these toroidal fibers. In the alpha LGQV framework, quantum vacuum energy is directly coupled to local matter density. Inside dense matter regions, the local vacuum energy is suppressed, allowing normal gravitational binding to take hold. Devoid of matter, cosmic voids retain their full, unsuppressed cosmological vacuum energy. In this framework, cosmic voids operate as highly energetic repulsors. The relentless outward pressure from these empty regions physically forces matter into the specific plateau foam geometry aligned with the Hopf fibers. The repulsive force of empty space provides the architectural confinement traditionally attributed to dark matter. This topological framework resolves a second, separate observational crisis in standard cosmology: anomalous preferred directions that challenge the universe's baseline anisotropy. Astronomers have tracked distinct directional anomalies across independent datasets, including the CMB dipole, the dark flow, the axis of evil, and quasar dipoles. Mapped on a polar projection, these anomalies don't scatter randomly, they cluster tightly within a 33-degree patch. Krieger's topology inherently possesses a global symmetry axis. The geometry dictates preferred directions align near this axis, while megastructures sit exactly 75.5 degrees away. Megastructures defying homogeneity and preferred directions defying isotropy are two symptoms of the exact same topological geometry. Any valid theoretical physics framework must generate rigid, falsifiable predictions for future datasets. This 3D co-moving map plots current data, but the upcoming dark energy spectroscopic instrument Full Survey will provide the definitive testing ground for the topology. The first prediction is the explicit detection of non-trivial linking numbers in filament pairs extracted from the cosmic web data. The second is global chirality, a statistically significant measurable asymmetry between left-handed and right-handed filament twists. Standard cosmology strictly forbids these signatures. In models relying on random initial conditions, accidental linking is functionally zero, and structures possess inherent mirror symmetry. The final geometric prediction is that dimensionless ratios, like void radius to ring diameter, will remain perfectly constant across redshifts lesses from 0.1 to 2. Ultimately, the entirety of the cosmic web appears to function as a rigid geometric constraint of our four-dimensional reality.